Guys, welcome back. We are continuing with the alkaloids. So we are doing that. How do we find out the structure of alkaloids? So we did a lot of different functional groups. Last one was alcohols. Now we are talking about carbonyl groups. So carbonyl, it is C double bond O, right? It can be aldehyde or ketone. We are not talking about acids or acid derivatives. Aldehyde or ketone carbonyl groups. So right now what we do in lab, I'll come to this first because this is what we do in lab. You add a little bit of 2,4-DNP and you get nice orange precipitate. So 2,4-DNP is 2,4 to position number 1, 2, 3, 4. So 2,4-dinitrophenyl hydrazine. Hydrazine is NH2. So when you react with it, react with aldehyde or ketone, this O and this H2. H2 is excluded. Is released and this hydrazone is formed, C double bond N NH, this one. You get nice orange precipitate. But this reagent was not discovered previously, and before they used to do a lot of other things, and still it is being done. So they would use hydroxylamine, so NH2OH. Very similar reaction, O and H2 is lost. You get double bond N OH. This is called as oxime. And then you can use this hydrazine, so NH2NH. A hydrazine derivative. Here you having C double bond O CS3, so it gives you semicarbazone. Same H2O is lost. Or you react with phenyl hydrazine, very similar to this, only nitro is not there. You'll get some characteristic color. H2O is lost and what you get is hydrazone. So hydrazine reacts with aldehyde or ketone and gives you hydrazone. Now once hydrazone is formed, okay, now it is carbonyl. So you have to differentiate between aldehyde or ketone. So now aldehyde, there is no conformity test for ketones, but aldehyde gets oxidized. Aldehyde actually is very fast, it oxidizes faster than alcohol, even alcohol. So what you do is oxidize and see if it is oxidizing, means it is aldehyde. If it didn't oxidize, means it is ketone, because we have already tested carbonyl. So what are the tests we do? We do two tests. One is silver mirror, one is Bendix reagent failing test. So silver mirror, you add ammonical silver nitrate and you put aldehyde and see if you get a silver color, silver mirror on the side of the test tube. So basically when you put Ag2O, it is Ag plus, okay. So Ag plus, this gets oxidized and this gets reduced. So this gets oxidized to carboxylic acid and this gets reduced to silver. So whenever you put down, it means precipitate. It forms a coating on the wall of the test tube. And similarly, when you do Bendix reagent test, you see color test. Both of them has the same principle behind them. We use Cu2 plus. So this gets reduced. It's a redox reaction. One thing gets reduced, other thing gets oxidized. So this gets reduced and this gets oxidized. And so you get a characteristic color. But because ketone does not have CH, CC bond you cannot break. It's very, very tough. So they do not give positive test for this reaction. Next is carboxylic acid. So carboxylic acid, basically you just add a little bit of sodium carbonate if you see effervescence, because carbon dioxide will be released, or you put ammonia. So when you put ammonia, we talked about these alkaloids. All of them were solid except nicotine, which was liquid, and few exceptions might be there, but generally it is solid. So you react with sodium bicarbonate and you start seeing that they are soluble in water. Previously they will not be soluble in water, but as soon as you add, they start soluble in water, and bubbling also will say, so you know that it has carboxylic acid. Similarly, react with ammonia, they form ammonium salt and become soluble in water because it forms salt. Previously, when you just isolated alkaloid, you will see that it is not soluble in water. And similarly, other thing is you react with alcohol, and if it gives fruity smell, this is what we do in lab. Carboxylic acid plus alcohol, little bit of concentrated H plus, catalytic amount we put and heat it. If you get fruity smell, it is carboxylic acid. What if it has carboxylic acid derivatives? So what are the carboxylic acid derivatives? Esters, just now we talked about esters, okay. Esters, lactones. Lactones are also esters but cyclic. Within the molecule, when it is cyclic ester, it is called as lactones. Similarly, amides, RC double bond O NH2. Yeah, RC double bond O NH R prime. And lactams is cyclic amide. So what do? You basically hydrolyze it and you analyze the product. So it can be acidic or basic. So something like esters. So acid esters you can hydrolyze. First you put base hydrolysis and put acid, you get RCOH and R prime OH, and then you realize what is it. You can just separately analyze them. If you have amide, same thing you can do, and you get a carboxylic acid and R prime NH2. Okay, but one thing you understand, it's very tough to hydrolyze amides. Esters very fast they hydrolyze. Here you have to heat for very high temperature in sodium hydroxide. Otherwise acid hydrolysis is much faster actually, rather than going basic hydrolysis followed by acidifying the solution, right? Now what if you have methoxyl groups? So if methoxyl groups are there, we find out how if it has methoxyl group, and if it has, how many methoxyl groups are there, by this method called as Zeisel's method. So Zeisel was a scientist. Okay, so Zeisel was a scientist. It's called as Zeisel's method. So you react with HI and you heat it. It's a very rough method. HI, you know, is a very powerful acid. It is much more stronger than HCl, HBr. Okay, so you react with it, and what happens is this basically goes and takes away the proton, and this I minus attacks this, and this goes away. So you get ROH and CS3I, and this CS3I you react with AgNO3. This is very interesting. This because carbon iodine bond is not strong. We have talked about inert pair. We talked about inert pair effect. In that time we said that as size increases, the bond weakens. Basically because iodine is too big, very big, the bond between them is quite weak, and so Ag plus attacks it and breaks it up and forms CS3NO3 and AgI. So AgI precipitates. So you can calculate how much amount of AgI is formed. You understand the logic. You already know the molecular mass of alkaloid. You have done starting CH analysis. You know everything. After that, you added excess amount of AgNO3, does not matter, but how much ever AgI comes, you find out gravitationally how much AgI is formed. So once you know, so you know how many moles are there, and you have already taken the alkaloid in exact amount. So you know how many moles of alkaloid was there. So with that you'll know that how much of OCS3 methoxyl groups are there. Okay, so HI and heat followed by AgNO3. Okay, next is nitrogen. Now nitrogen can be amide or amines generally. If it is amides, we saw that acid derivative it is, we do those. If it is amine, it can be primary, secondary or tertiary. How do you find out? How do you differentiate rather? So what you do is you react it with CS3I, and you see how many moles of CS3I is being consumed. Now you already know the atomic mass of your alkaloid, so you add 1 mole of it according to how much ever you are taking. 1 equivalent of that you take CS3I. If it consumes and reaction stops, so you know that it is tertiary amine, because 1 lone pair is there, it attacks CS3, I minus comes out, and you get quaternary ammonium salt. Because when you react with CS3, it will not stop at secondary or tertiary, it has to go to quaternary. If it is secondary amine, first it goes and react, it forms NCS3 plus, then even this proton NH bond breaks and you get another CS3 added. So 2 moles of CS3I are being consumed to form again quaternary ammonium salt. Similarly, if it is primary, so this was secondary amine, this is primary amine, and this is tertiary amine. Okay, so this is tertiary amine, this is secondary amine, and this is primary amine. Okay, and you get this. And one thing is, it's tough to find out that how much you added, how much when the reaction stopped. So what you do is you allow the quaternary ammonium salt to be formed. Now you have added CS3I. So you see how many CS3 got added. CS3 got added. If 3 got added, that means you know it was primary. If 2 got added, means you know it is secondary. If 1 got added, means it was tertiary. And how do you know? Once you form this quaternary ammonium salt, again you react with HI, and this CS3I will come out, and again like Zeisel's method, you react with AgNO3, AgI will come out. You estimate how much AgI is formed gravimetrically. So once you know how much AgI is there, you know how much amount of CS3 has come out. So you know exact how many OCS3s were. Sorry, what was the primary, secondary or tertiary amine. Next is degradation of alkaloids. So degradation, you see now this is like you hit it with real hard bullet and let whatever breaks, no problem. You'll get some very very simple molecules whose structures are already determined. So you compare the physical properties. I am talking about time before NMR spectroscopy was there. Okay, so it's like very hard methods. You find out some molecule and try to figure out it matches with physical property of which known molecule. So even if you know physical properties, very tough to compare. Okay, so some of the basic compounds, if they compare and they see that it is having same physical properties, then they know, okay, at the end it forms this. So you know this is the skeleton which the molecule has. Okay, so it is more of a just hitting hard and breaking up everything, and whatever is left with that we try to figure out what kind of skeleton it had previously. Okay, so first one is Hofmann elimination. Hofmann elimination gives you some idea. What it gives you idea? It gives you idea that it is amine, and gives you idea that beta position it has hydrogen. Okay, so you basically react with methyl iodide to get quaternary ammonium salt. We saw even if it was primary, secondary or tertiary, all of them will react with methyl iodide to give you quaternary ammonium salt. Just now we saw. Okay, and then you react with AgOH or Ag2O, it becomes hydroxide, and then it cleaves. So if it cleaves, you know for sure that there is a beta position hydrogen is present. Okay, so this is the amine part, so alpha beta. So this is how reaction happens, and we also know that the hydrogen is in trans antiparallel position. What I am trying to say is, if this is a rigid ring, then if hydrogen is not in anti position, this elimination will not happen. So mostly when it is open chain, then only it happens. So you get some idea how the molecule may look like. So like this example they have taken. So because here rotation is possible, so hydrogen can come in your trans anti-parallel position, and then this can break up. So they react with CS3I, you get quaternary ammonium salt, and they react with AgO, and you get OH minus, and then it cleaves up. Okay, and yeah, so this is the known example which they would have done. Okay, so this is the alkalide, and then finally what you're getting is para-methoxy styrene. So now you know styrene, it was in news a few days back. Styrene was the one which came out of the chemical plant in Telangana, and so many people died. Okay, Hyderabad. So this is para-methoxy styrene. So this is also very common molecule they knew, and that's how they found out of this alkaloid, right? Then the next one is Emde degradation. Now this is for those amines which do not have beta hydrogen, and therefore does not undergo Hofmann degradation. Okay, so here what you do is, like, see this nitrogen, it does not have beta hydrogen because this part is blocked, this part is also blocked. Okay, it has, but this is a ring. Okay, so if you want to break this part, you have to use some other method, because Hofmann will not break it. Hofmann will break here because this proton will come, this is beta hydrogen, so this will come and this will break up. I want to break up. Why I want to break up? Because finally I want simple molecules so that I can analyze. So I will try to possibly break this and then possibly break this also. So previously, like, we know this is the structure. When you don't know structure, you try to break. So you break first with Hofmann, it broke, but still nitrogen hanging around. You want to get out of it. So you use this method. So here again you react with CS3 excess. So because here it was secondary amine, you can see hydrogen is there on the nitrogen. If zero hydrogen, then it is tertiary amine. When one hydrogen, secondary. When two hydrogens, primary. Okay, so it react with CS3I and you get tertiary iodide, and then similar to Hofmann, you are reacting with AgOH, you are getting O minus. Then what you do is, there you are just heating up. Here you have to use sodium amalgam or sodium liquid ammonia, that is Birch reduction. So here we are showing sodium amalgam. So when you use sodium amalgam, this one breaks out, which does not have beta hydrogen, breaks up. This is Emde's degradation discovered by Emde. And then you do Hofmann, and Hofmann, this will come out and this will comes out, and you get this styrene. So this styrene structure is very common. So you know that the alkaloid which you took had styrene kind of skeleton. Okay. Now last one, that is von Braun's degradation. This is for two groups. One is when tertiary cyclic amines and secondary cyclic amines. So tertiary cyclic amine, how do you find out? Using this von Braun degradation. So you understand this, you are starting with a material whose structure you don't know. You are putting some things and trying to find out. So you react with cyanogen bromide, CnBr, okay? Cyanogen bromide. So nitrogen attacks this carbon, Br minus leaves, and you get this one, Br minus. And then using HBr and boil. See, very, very rough and tough condition. HBr is a very powerful acid. You should see in lab. When you open, a lot of fumes comes out. It's much more bad than HCl. Okay. And then what happens is it breaks up. Is basically HBr is there. This Br minus attacks here and this opens up, and you get this molecule. So what we are trying to say is it will break up tertiary amine. Okay. So it says where Hofmann was not possible, there you do it. And even if Hofmann is possible, when you do Hofmann breaks different way, this one will break different way. So and Hofmann is applicable even for acyclic opened amines, but this von Braun's degradation is not applicable for open chain alicyclic amines. Only for cyclic amines it is possible. So simply like it is saying for this molecule, when you have this, when you do Hofmann, what will happen? Beta position, this will break up, right? Here alpha is there, beta there is no hydrogen. So beta hydrogen, this will be taken, this will come out, and this will come out. First step is same for both of them. You react with CS3I, so it forms tertiary amine. Whereas in von Braun, what happens is it breaks up here. There is no taking out this. You know what happens? You put CnBr, so Cn comes attacks here, and then Br minus goes attacks here, and this comes out, and you get CH2Br Cn. So this structure you get some idea. You break it up, right? Now when you have secondary ring, so here, right? So when you have secondary amine in the ring form, cyclic amine, secondary cyclic amine, you react with benzoyl chloride. Okay, it is benzene ring, pH, C double bond O Cl. If it was pH CH2Cl, it is benzyl Yl. Okay, when it is C double bond O, it is benzoyl. Okay, so it is benzoyl chloride. You react it with this, and this nitrogen attacks here. This will come up, this will go away, and you get this hydrogen is taken away. And then you react with PBr5, you get this intermediate, this double bond O is lost, and 2Br get added, and you're still under reduced pressure. This whole thing comes out, and then bromine gets added. You'll say, what's the purpose? The purpose is making it a simple molecule. This molecule you can recognize. This molecule will be very, very complex. So molecule you don't know what is it, but you are able to break and try to tell how many carbons were there in the ring. 1, 2, 3, 4, 5. If 5-member ring, 6-member ring, all that you can do, right? Next is reductive degradation. So this is very useful reaction for reducing carbon skeleton again. See this, how hard you are hitting. You are taking this, this is a pyridine, but it's just an example, like anything could have been. It could have just a pyridine ring in the whole alkaloid structure. You are heating with HI, very, very, very powerful acid, very strong acid, okay? When 300 degrees Celsius, and you break up everything, ammonia is lost, and you're left with 1, 2, 3, 4, 5 carbons. So you know that something was there which had 5 carbons. So you get some kind of structure. Similarly, they have taken this molecule. I think this is atropine. I know this molecule. Okay, I'm not able to get it. They synthesize this molecule with Mannich reaction, mostly atropine. Okay, I'm not getting the name, but yeah. So when you react with this, this breaks up first and then goes off. Everything goes. See, this OH is gone, forms HI. You understand? HI is very powerful acid. This oxygen will go and attack hydrogen. it becomes H2O plus, and this I minus attacks, H2O is lost, and then this CH3 also breaks. Finally you're getting 7-membered ring. Now cyclohexane, cycloheptane, everybody know all the characteristics, so you are able to know that the starting molecule had 7-membered ring, right? And next one is zinc dust distillation. So again, this is a very rough method. Here what you do is you put lot of zinc dust. Okay, zinc dust, you know, reduces. Not exactly reduces. It does a dehydrogenation. It removes hydrogen. Okay, and eliminates oxygen if anything is there. So they have given example. They did with quinine. This is one of the alkaloid, and they put zinc dust and distill it off. Okay, and distillation not even under low pressure. You just distill. You put a lot of temperature and distill it off. So what happened? All these hydrogens are gone. You get this, and all this we are doing with expectation that it comes out with some structure whose structure is already known. So once you know this, okay, you know that some kind of structure is there which had 6-membered ring and this. Similarly, when they reacted with ricinin, they got pyridine, right? See, they will have no idea about this, but they will know that it was 6-membered ring with a nitrogen. Pyridine, it has some 6-membered ring with nitrogen. And some things they will get idea because OCH3 they will use Zeisel's method. C-double-bond-O they will use all that tolerance reagent, things like that, right? 2,4-DNP. Then alkali fusion. Fusion means, you know, fusion means melting. So alkali means you take pellets of sodium hydroxide or pellets of potassium hydroxide and heat it up. No water. Extraordinary rough condition. So when you do this, so alkaloid breaks up into small pieces, and then you try to figure out how it was. Okay, there is not much logic, but you very rough condition, but it was time when we didn't have soft all these machineries. So whatever is possible you do and try to find out what it is. So they have taken this example. So this alkaloid they took and they heated with KOH pellets you put and just heat it up. No water, just heating at very high temperature, and whatever breaks up, and they broke up and they saw the structure. So this structure was not very common, they didn't know, but this structure they knew because everybody, you also know it is quinoline. So once they separated it out, they find out there is quinoline. So they knew this alkaloid had quinoline molecule in it. Okay, thank you.